right? The material in this book, some sections become pretty abstract, involves proofs, and sometimes this is just very special examples. So no theory about that. We just need to do some calculations. In the last class, I was talking about level surfaces, right? Level surfaces, and it's about some functions in three-dimensional space, right? So the level, remember, the levels are given function x, f, x, y, z on some open domain, U inside R3. This is right, and then this is called level surfaces S, right? S is going to be defined by this equation, okay? So when F equals K, you get 7. Now the question is whether this is going to be a smooth surface. Yeah, all I have to do is make sure, if the gradient, okay? If the gradient is not going to be 0 for any point in the surface, then S is a smooth surface. Right? Yeah, that's what the film says that. And actually, you can solve for roughly you can view this as a graph of some function. Now, what does it mean? The gradient of the function, right, is going to be the partial derivative, right? So this is not going to be 0, means one of them is not going to be 0, okay? Yeah, if at some point this is not going to be 0, then one of them is not going to be 0. So you can assume that this is not going to be 0, okay? If this is not going to be 0, then in the neighborhood, is not going to be 0, okay? So that means you can solve for, and actually one can solve this equation for z, okay? And then you can get z is going to be, well, I can use any function again, okay? So such that, okay. And so that's what I say. So the surface, for that portion of the surface, is the graph of a phi, okay? For that portion of surface. Yeah, so for z for x, y close to that point, okay? Okay, then you can, this is an open set, right? But then there's a small open set we call W, okay? So in other words, there's a W, an open set W at, right? Such that the surface, okay, is a graph. It's a graph of phi, okay? So the surface of the level surface actually consists of graphs of some functions, okay? And if the partial derivative f with respect to x is not going to 0, you can solve for x in terms of y, z, okay? So that's the idea, okay? Now we are going to consider a special function, which is called the quadratic function, okay? We're going to consider this type of function, okay? They are in the form a1 x squared. So it involves squares. Consider, let me erase this. A1 x squared plus A2 xy plus A3. No, I have more than that. Okay, A1, A2, A3. Then have lots of coefficients. It's better to use some other notations. Okay, so I'm going to. What am I going to do? Yeah, I'm going to use A11. Okay, x squared. Okay, A22 y squared. A33 y z squared. Okay, and then I also have a mixed term A12 xy. And we may assume that xy, yx is the same, so I put twice here. Okay, then twice of A13 xz, twice of A23 yz. Okay, then plus B1x, B2y, B3z, and plus constant c. Okay, so there are many, I get all the terms here. So this actually can be written in the form, in the matrix form. Okay, I have A11, A12, A13. Okay, A21, A22, A23, A31, A32, A33. Okay, and then plus B1, B2, B3, X, Y, Z, and plus C. Now, this is going to be symmetric matrix. So A21 is going to be A12, A31 equals A13, A23 equals A32. Okay, so it's a symmetric. So this is a quadratic, right? Quadratic functions x, y, z. Okay, this is called the quadratic function in x, y, z as most general form. Okay. So the question is, what kind of level surfaces does that look like? Then it depends on the coefficients, of course. Right? Now, it's not easy to check whether this is the level surface is a smooth surface. Right? You may not be able to solve it. You probably can solve it always, yeah. So consider this to be K. Okay. So you get the level surface, right? The level surface determined by this equation. Now, then you have to check whether the gradient, okay, is going to be zero. If the gradient is not going to be zero, then at those points, then this is a regular point, okay? Right? And every point is a regular point, then it's a smooth surface. So we calculate the derivative A11x. Any other terms involved? Yeah, A12 y, A13 z. I think then I have a plus v1. You see? Yeah. So you get the linear equations. Twice of A22y, and which term containing y variable? Let's go back to look at A12 x. And I think it's 2A23 z, because it's yz, okay? And the plus b2. A33z plus twice of 1, 3x, twice of 2, 3y, and b3. So, so you get a system of linear equations, and you get a unique f. When you set this to be 0, more like you're going to get a unique solution. And I think yeah, okay. You have x, y, z, that's y. x, y, z, yeah, z, x, y, okay? So in general, it's still complicated, you know, if, yeah, if all those equations, right, those are the linear equations, and you can, actually, that's only one point. In general, there's only one point satisfying all those, so that all those partial derivatives zero. Sometimes just only get 1 point. If that point is not on this level surface, then this level surface is a smooth surface everywhere. If this point happen to be on the surface, and there is a one singular point, if you remove that singular point, you get a small surface. Okay, so in general, okay, in general case, yeah. So you consider this equation, okay. In general, there's okay. In general, there's a unique solution to the above system. Okay, x0, y0. Okay, satisfy solution to this equation 1, 2, 3. Okay, because this is system of linear equations. As long as it's not, you know, that's just in general. Sometimes you have infinite solutions. So in many cases, it's just only one solution. If it's only have one solution, then this is a point, okay? Then the level surface, okay, is a smooth away from that point, because at that point is all the partial derivative zero, right? So this is the level surface. Here's in space. Okay, this is a well, the function is defined everywhere, so don't need to worry about it. Okay, so the domain. Okay, so you have a surface, the level surface, right? Those are the level surface. F equals k, and this is a point, maybe here. So there's only one surface passing through that particular point. And then even that surface, it's smooth everywhere except for that point. You see? Except for that point. Okay? But the other surfaces, okay? Other surfaces, there's no single point. Smooth everywhere. Okay? Possible. It's a singular point. Right? Yeah, sometimes I'll give you an example. Okay, example. Okay. The example. Okay, here's the example. F of x, y, z is going to be x squared plus y squared minus z squared. Okay, right? All right. So this is and then you look at the partial derivative, right? Partial derivative is going to be 2x. Partial derivative is 2y. Partial derivative with respect to z is 2z, right? So when you set this to be 0, there's only one solution, which is x, y, z is the origin, right? Only at that point, those partial derivatives are all equal to 0, right? So in other words, the gradient of f is not going to be 0 for any point away from, right? All right, so take a look at the value of this function at this special point. So that means it's going to be 0, right? All right. Okay, so let's consider this equation. All right, so that means x squared plus y squared minus z squared equals k. So z squared equals x squared plus y squared minus k. Okay, when this is going to have a solution. Okay. And yeah, this is surface, right? SK is determined by this equation. So if K is not going to be 0, okay, SK is a small surface. Why? Because the gradient is not going to be 0, because it does not contain the origin. Okay, it does not contain the origin. Okay, if K is not going to be 0. Now that's a possibility. What happens when K is negative? When K is negative, it's this is defined. Yeah, it's defined for every x. Okay, when if K is negative. So let's try to draw the graph. Okay, I hope I can draw it. X-axis, Y-axis, Z-axis. Okay. So what happens when K equals 0? When K equals 0, I get a cone. I think I get a cone. So when K equals 0, I get a cone. Okay, and then there's one singular point here. This is a singular point. Right, when K equals 0, the graph passing through the point where the gradient is 0. So that is a singular point. Okay. Now when K is less than 0, okay, then this is a Z is if K is less than 0, Z is going to be plus minus square root x squared plus y squared minus K. It's defined for every x, because inside is never be negative, because K is negative, so minus K is positive. So how does it look like? This looks like that. That's two pieces. Okay, K is negative. Now, if K is positive, then there's trouble. If K is positive, you're still trying to solve for Z. But this is not defined for if X, Y too small. Okay? If K is positive, maybe, when it's going to be 0 or negative. And this is going to be something like that, a circle, okay? With the radius I equals square root of K, okay? Square root K, okay? So, so I'm going to draw the picture again. And this is a special cone when K equals 0. When K is a positive, okay, there's a circle here with radius I equals square root K. And inside of this circle, Z is not defined. Outside this circle, I think Z is defined. So there is a plus minus part. So the graph looks like that. Okay, can you understand, right? This is a picture. All right, so it's defined and the plus minus. Right? Yes. Guys, this is a circle. Yeah. The graph is not defined, okay? Inside. And there's it's a smooth everywhere. Okay, it's a surface. Right. So that's when K is greater than 0. Okay. So there's a circle here. Is going to have a radius equals square root K, square root K. So this is a nice smooth surface. Now, how to parameterize a surface? Yeah, that's a good question, right? How to find the one parameterization? I don't think so you can do that because it looks like a cylinder type, but it's curved, right? Right? And it's connected. But when K is negative, you get two pieces, okay? You get two pieces separate, disjoint, right? You get two pieces. Then you can find parameterization for each pieces because these two pieces are graph of function on x, y, z. So it's easy to find the parameterization. Right? And topologically, each piece is just R2, right? Because it's just curved R2, right? Curved plane. So that's different from the one here when k is positive. It's a cylinder type, right? It's because this kind of surface is called surface of revolution. Okay, surface of revolution. And we're going to start the next section. All right, now from linear algebra, okay? From linear algebra, you can, let's go back to this equation, okay? This is you have A11, A12, A13, A31, A32, A21, yeah, A23, A31, A32, A33. This is the most general one. But you can use a substitution. Okay? Eventually, you can diagonalize this matrix. Okay? And if the eigenvalue of this matrix will be lambda 1, lambda 2, lambda 3. So you can find a linear transformation to x prime, y prime, z prime, okay? Such that, yeah, let's use a tilde, okay, tilde. Okay. Such, this is linear transformation, okay? Such that the above matrix, above equation is simplified to this. Okay. And this will be B1 tilde, B2 tilde, B3 tilde, and the X tilde, Y tilde, Z tilde, and the plus C tilde equals 0. Okay. Then are we able to simplify this one a little bit? I think the answer is yes. Okay. And then it depends on the sign. Okay, I just want to show you one example. Okay. So here, lambda 1, that's a step 1. Okay. Step 1, when you're trying to simplify, you find the linear transformation. Actually, this is a orthogonal transformation. Okay? Every matrix, symmetric matrix, okay, there's an orthogonal matrix, okay, such that, yeah, this is a factor. Let me be quiet. So if A is a symmetric, the transpose equals A, then there exists an orthogonal matrix okay, O, such that O transpose A and O is going to be the lambda, if it's n by n matrix. Okay, this will be diagonalized. Okay, and then use that O, you can get right. So so what I'm going to do is look at the matrix. Okay, here's X, Y, Z, right? And this A is because it's orthogonal matrix. So the transpose is going to be the inverse. Okay, it's the same. So that's why this matrix is going to be O and lambda 1, lambda 2, lambda 3, and O transpose. Okay. Yes. So that's why X, Y, Z, and here X, Y, Z, and you replace by O, lambda 1, lambda 2, lambda 3, and here O prime, X, Y, Z. So this part is just called X bar, X tilde, Y tilde, Z tilde. That's all you need, okay? So you are X tilde, Y tilde is obtained using this O. Okay. All right, so that is guaranteed. Now we have a lambda 1 x to the square, lambda 2 y to the square, lambda 3 z to the square, b1 to the x to the, b2 to the y to the, b3 to the z to the, and plus c to the. Okay, so that's going to be 0. Now, are we able to? We have a 2x here. Actually, as long as lambda 1 or lambda 2 is not going to be 0, then you can get rid of the linear term. How do we do that? Okay, if lambda 1 is not going to be 0, okay, then what are you going to do? Lambda 1 x to the plus b1 to the x, right? This you can take lambda 1 out. Okay, right? Now you want to complete the square. So if you want to complete the square, you have to, I think you have to add half of that square. So that will be twice. Okay, and plus b1 to the 2 lambda 1 to the square. And you have to subtract it because this is identity. Okay. Then those three terms can be combined. That is called completing the square. Okay. And you multiply minus actually. Minus lambda 1 time, this is not lambda 2, just lambda. Okay. So you have a lambda, and that's going to be b1 to the square, and here 4 lambda 1. So those two terms can combine into 1. Then you can introduce another variable. So you can let x bar to be x to the plus b1 to the and 2 lambda 1. It's not a lambda 2, there's no 2 here. All right. Then you will get x1 lambda 1 square and the lambda 2 x2 y to the lambda 3 z to the and the b1 to the is gone. Okay, so you get b2 to the y, b3 to the z to the, and the plus this c will be changed. That's why I put the c bar here. Okay, yeah. Okay. See, then it's step by step, and then it really depends on whether you're going to have whether this is 0 or not. Maybe this is 0, then you stop there. If not, then you can get rid of this square. Okay, get rid of y to the is a linear term. Those linear term can be get rid of only when you have a y to the square and a z to the square in the equation. Okay. So in the book, they give you a list of those standard forms. So this is a second step, right? It's a second step. How do we get rid of the linear term? Okay, sometimes you can get rid of, sometimes you cannot. Okay, and for example, if we already have a 2 square and the y square and the plus, I think, and the 3z plus 5 equals 0. Now in this case, you are not able to get rid of z because there's no z squared there. Okay? Okay. So you cannot get rid of the linear term. You cannot get rid of the linear term. Right? You cannot get rid of the linear term. Okay, it cannot be simplified further, but what we can do is you can combine those two. Use you can take 3 out. Final touch we call it, plus 3 z plus 5 3 equals 0. I can introduce z bar to be z plus all those transformation we call the orthogonal transformation or translation. This is a translation, right? Okay. This is called the translation, and here is also translation. Okay, this is a translation, and this is actually called a rotation. Right, you rotate the vector, by this matrix. Okay, you rotate the vector by this matrix. All right, and then what you get? You get 2x squared y squared plus z bar equals 0. Okay, rotation and translations that do not change the shape of the graph. Okay, just rotate the 3D picture in the space or just move around, but does not change the shape of the graph. That's why we prefer this kind of transformation. Okay, and then if you don't want to change the shape of the graph, and this is the simplest one equation you can get. Okay, and or you can write in the form like this: negative 2 over 3x squared minus 1 over 3y squared. Okay, so how does the graph look like for this one? So right now, here's x, this is y, this is a z bar. Okay? In this new system, this is a kind of like a paraboid. It touches the vertex. Okay? Right? Touches the origin. Okay? It opens downward. Each section its cross section is elliptic. Okay, elliptic, not a circle, because the coefficients are different. So this is a elliptic. Okay, and this is a circle. Okay, this how does it look like? Okay. All right, so there almost involves 3 steps. Okay, the last step is to work on this linear term. Okay, work on this linear term. Then do another translation. Okay. So let's try another problem. I think the difficult part is to find the orthogonal matrix with a rotation. Translation is easy, right? Translation is easy to figure out. Okay, let's take a look at this one example. And x squared plus y squared. Okay. I'm trying to see why my pen is let me draw with a thickness. Yeah, like this thing. All right. So x squared plus y is this. Yeah, let me check this. But yeah, I like this. I can try this. Okay. X squared is better. Y squared minus minus 2z squared minus 2xy plus 6z equals 0. Let's take a look at this equation, okay? Now, how much we can simplify? I think we already finished the, no, we haven't finished this part. It says there's x, y there, right? So if you want to write down the matrix, those three terms looks like this, x, y, z, okay? And this is the x, y, z, and plus 6z equals 0, right? How can I get, this will be -2. I think that this should be 0, 0. Okay. Then I get to 1 and 1. I'm pretty sure this is also, this is a minus 1, minus 1. Yeah. Okay. So this is a matrix. You have to make it a diagonal, but that takes too much time to do that. Yeah, this requires linear algebra, right? Now, yeah, let's see. X, Y, 1, -1, -1. X, Y, that's going to be, you know, x minus y, -x plus y, and xy. So you want to multiply this out, will be x minus y x plus -x plus y y. So that's why you get x squared minus 2xy and plus y squared. Okay. All right. Yeah, since the question is, what kind of matrix you're going to get so that you're going to get the two eigenvalues, right? Are we able to simplify this? Okay. Now take a look at the eigenvalue, okay? Sometimes you cannot do that, okay? The eigenvalue, we'll take a look at the eigenvalue. So the matrix lambda, 0, 0, minus 1, -1, -1, and that is going to be lambda minus 1, 1, and 1, lambda minus 1. So the determinant is going to be -1 squared and -1, okay? So actually, you get lambda squared minus 2 lambda plus 1, so you have a 2 eigenvalues. That's great, right? So you have a 2 eigenvalues, so 1 should be equal to 0, other one is going to be 2. So you have to find the matrix. Yeah, you have to find the matrix, okay? I hope you remember the algebra. Okay, so when the lambda is 0, right? And I just need to find the eigenvalue, right? Eigenvalue, so it's going to be -1, 1, -1, and UV, right? That's supposed to be 0. Right? This will be the eigenvector, right? So clearly, U is going to be negative U plus V should be 0, right? So so UV should be UV should have the same sign. Now, since you have to have a unit vector, that's why it's going to be why have to be unit vector, because we're going to look for the orthogonal vector. Okay. Okay. This is a unit vector. Okay. Then when lambda equals 2, okay, and the UV. Okay, in this case, I get 0, 0. So clearly UV should have the, oops, where's the, change it back. Okay, so U plus V should be 0. So clearly UV is going to be, to have the opposite sign. So I can assume that. Right. So now you have a two matrix. Okay. So this is a one negative one, one, acting on those two. This is going to be 0. It's eigenvector. And the other one is negative, and that is going to be 2. Okay. All right. So if you put together, okay, you are able to get, I think, 0, 0, 0, 2. Okay. If I call this O, this is A, right? So this matrix is going to be this O, 0, 0, 0, 2, and that O prime. Okay. The inverse is also O prime. So this is our decomposition. All right, then clearly, you know, if you put the both sides, put the X here, X, Y, right? Don't worry about Z. And this one, negative one, positive one here, right? And here, X, Y. Okay. So clearly, this is going to be X bar, Y bar. So you can write down the transformation. So X bar, okay, Y bar is going to be X, Y. Okay. So let's multiply this out. I think that's it. So if you're using this transformation, then the above equation will become, it could become very simple. Okay, so you will get, yeah, you will get, what you get here, using this equation, you know, my problem here is this part, x squared plus y squared plus z squared. That's a standard form, okay? So x squared plus y squared minus 2xy, okay? And that's going to be x bar, y bar, 0, 0, 0, 2, right? X bar, y bar. So that is going to be just 2y bar squared. And that is true, right? So 2y bar squared, as you can see that, right? And that is just x minus y squared. It's the same. You know, you can get this quickly, but that's computation. Okay. So oh, there's my file. Okay. So then there's no changing on y variable. So our equation, so the equation becomes yeah, the equation becomes 2yz bar. Okay. So the equation is 2yz squared plus minus 2z squared. Okay. And I forgot the last term. Plus 6z, I think. Yeah, plus 6. Okay, 2. Yeah, okay, plus 6. Right. Then you have to take a 2 out. That's easy part, you know, right? Right. Then completing the square. So it will be z plus 3 over 2 square minus 9 over 4. I skip a little bit. Okay. So I get, if I let z bar to be z plus 3 over 2, this is a transformation. Then I got 2y bar square minus 2z bar square and plus 9 over 2 equals 0. Okay, then you divide both sides by, well, it depends how you do that, right? So if you express the divide, you know, if you move this term to the right hand side and divide by negative of this number, then I got the following. Okay, I think I got z squared. Oh. Why it's not stable is yeah. So yeah, it's going to be 2 over 3 squared, okay? Minus y bar square over 3 squared equals 0. Okay. Now, in the, how do you sketch this graph? Sketch the graph. So this is the x bar, that's the same as x, y bar, z bar in this coordinate system. Okay. So in the YZ plane, this is a hyperbola. Right? This is a hyperbola. And when y equals 0, this is going to be, this hyperbola looks like that. Okay. Does not intersect with the y. Y could be, this could be. Okay. And then there's no restriction on the x, so the graph looks like that. How can I draw the graph? Okay. Yeah. It's harder to draw it. I hope you understand. Okay. Okay. So there's another piece down there. All right. So this is a regular surface, and it's called a hyperboloid. So it is a hyperboloid. Right? You can eventually you can simplify the equation to the one of the standard form in the book. Right? One of the standard form in the book. Now let me talk about the other surfaces. So that's section 5.3. One is called ruled surface. A ruled surface is like this, given curve, and then a bunch of lines form the ruled surface, okay? So how do you make it? You know, you have so many pieces board, okay? And then, but there's only one line in the middle, you connect them. Then no matter how do we twist, you get surface. And those kind of surface called the ruled surface, all right? So first of all, yeah, you can, on the ground, you put a piece of line, right? Then, then you can evenly put the lines here, okay? But when you lift this side, then they're twisted, right? So twisted, then you always get surface. And this kind of surface is called the ruled surface. Now, how do you describe it? And when is this is a regular surface, okay? I'm going to try this. This is arbitrary curve, okay? So it's called gamma. I'm going to call it U, gamma U, okay? I may also, you can assume that U is a arc length of the curve. It's okay. Then along the vector, I have I'm going to use have to use another vector field, right? So this is V is going to be this can be any vector. This can be a normal vector or could be something else. Okay, if you want to keep it perpendicular to the curve, so V and U. I'm not going to use a V because otherwise it's confusing. Let's use a delta. Okay, delta U. Delta is also vector. Okay. Okay. Then this ruled surface sigma can be described. Here's U is between A and B, right? Okay. Then this is going to be on the U. U is going to be actually is A and B, but close up. Okay. There's no restriction on up. But if there's no restriction on the second component, maybe it's possible somewhere you're going to get a single point. Okay. So sigma UV is going to be gamma U plus V delta U. Okay. Delta U is just a vector field along the curve. So that's why it depends on U. Okay. So is sigma regular? When it's regular? That's the question. Okay. How do you check whether it's regular? You have to look at the partial derivative. No, two down here. Right. And this is still V, okay? And the sigma V is just delta U. Okay, so when they're going to linearly independent, okay, when they're going to linearly independent, it depends, okay? And it's not clear, right? So it's not clear whether this is going to be zero or not. Okay. So sigma is regular if only if this is not going to be zero. Okay. This is a question. So when it's going to be zero. Okay. Right. So let's take a look at a special case. look at the special case. Look at the special case. We assume that. Oops. We assume that gamma is parameterized by the arc length. How about this? And the sigma delta is going to be the normal vector. Okay, it's a normal vector, one of the normal vector. Okay, so n. Okay, there are two possible ways. Delta can be the normal vector, can be tangent vector. So there along the curve, there are three vectors you can choose, right? Along this curve, right? So we assume that this is a gamma, right? We assume that gamma is the arc length, right? So so you actually have three vectors, n, right? This is t, that is n, right? T and the n. I think how can I do it? T and n, the inside that's a b. B is a t cross n, right? Remember this. So my I can choose any of them. Okay, so we can let delta u to be. Let's use this one. How about this? Okay, let's use this. Okay, then okay, remember gamma prime is going to be t u, right? Okay, and the delta prime u is just n prime u, right? So do you remember what is that? This is actually, there's a two quantity here. Right, there's two quantity. One is negative. I forgot this is yeah, okay, here it is. Yeah. Okay. So that is going to be negative curvature plus torsion. Okay. So let's put it back. Okay. So sigma u cos sigma v. The first one is a t cross delta, t cross n. Okay. So I'm not going to write uv always. Okay. Well, I should use it. Okay. T cross. Wow. Come on. I need to change it back to sigma. I don't know why. NS NU plus V. Delta is N prime U, right? Plus NU. Okay. Now it's easy. T times N is going to be B. Okay. And that is negative K TU plus tau BU plus NU. Okay. So you will see BU T times N. So it's KV and T times N is BU, right? And then V tau B times N. What is B times N? B times N, suppose it's a curvature. Yeah, let's see. If this is a T, this is an N, this will be B. Okay, if B times T, B times C, it should be N. Okay, B times T should be N. T times N is B, and the B times T, B times T is an N. Okay. Right, so now it's clear that 1 minus KV BU. Right. So when this is not going to be 0, so if the torsion is not the 0, then this never be 0 for V is not going to be 0. Right? Right, so my conclusion is that if, sorry, what happens? Yeah, if tau is not going to be 0, if there's always torsion here, and then I think this never be 0. Why? Well, even V0, but V0 the first term is not going to be 0, right? Because it's 1 minus kV. So this never be 0, okay? So when tau is 0, this not be 0. When tau is not going to be 0, then when tau is 0, okay? When tau is 0 at some point, then V cannot be too large, okay? Because, yeah, sigma u sigma V is not going to be 0 if K U V is not going to be 1, okay? This is this have to assume those it's not so curved. So there's some possibility there was some points there. So at least the V cannot be too large. If V is small, is okay. So it's guaranteed if V is small, then this is always surface, okay? It's always regular surface. Okay, that's, you know, if V is less than 1 over K U, okay? And then, oops. Yeah. Okay. Then sigma U, sigma V is not going to be 0. Okay, I don't know what happened to my pen. So they're not going to be 0. Okay. All right. Now, this is a type of surface called the lunar surface. Another type of surface is called the surface of revolution. The surface of a revolution is generated by the following curve. Okay. So first of all, I draw the curve in the YZ plane. Okay. So this is a curve in the YZ plane. How can I describe it? This is a gamma. I'm going to use a gamma u. Okay, gamma u is going to be the first component 0, and that is I can use okay, I can use yeah, I can use F U and G U. How about like that, right? So this is in the YZ plane. Okay, you can start with the XZ plane. It's okay, right? You can start with the XZ plane, then I don't know. Maybe better use in the XZ plane first. Okay, because no computation here. So that's the formula. Now I change it back to back. Okay, thickness. Okay. All right, let's use this one here. Okay, so that will be X will be F over U, Z G over U. Okay. Then I rotate along the Z axis. Okay, I get surface like that. So the question is, how can I get parameterization? Sigma, right? Right, have to write down U and V. I think the last component is not you have to describe a cosine, right? So Fu cosine V, Fu sine V maybe GU, right? And then V's right? Then you rotate. So when you fix U, you get the same level. It's a curve. It's a circle around this y-axis. Okay. So that's it. U is if here U is between A and B, then this one be U is between A and B. V is between between 0 and no restriction of V. But if we maybe I just choose this one. Yeah. Then this is a surface patch for that. Okay. Then sigma is a regular patch. Regular surface patch. Okay, for the surface. Okay. So let's check whether this is going to be regular now. Okay. Let's check. Okay. Yeah, let's check this. Differentiate with respect to U. Okay. And that is going to be negative Fu sine V, Fu cosine V and 0. So cross product, and this will be IJK. So let me write down the first component. The first component will be negative F U G prime U cosine V. The second component it's also minus F of U G prime U sine V. The last component is going to be F prime F U. Okay, so those are the components. This is a questions of whether this is going to be 0. So let's just look at the norm. Okay, the norm square is going to be Fu square G prime U square n plus F prime square F U square. So you take Fu square okay. So in general, we always assume that F of U is positive because we're going to rotate it along the z-axis. In this case, it's regular if only if the derivative is not 0. Okay. So you can tell when it's not going to be, this is going to be regular. So that you determine the condition when it's regular. Okay. Then you can compute, later on we are going to study the curvature, introduce motion curvature. Then you can use, once this special surface patch is given, then you can use that to calculate the curvature. Okay. So now what happens when this is going to be 0? Okay. So look at this is identically 0 if only if F U equals G U equals constant, right? They're both a constant. Constant. What kind of constant could be? Okay. So how does that look like? if the derivative is okay, let me go back. Did I make mistakes, computation mistakes? I possible, no? So if u is a constant, and this is not going up, it's just one point. It's just a circle. How could it be this? Okay, let me double check my computation. My computation is correct. All right. Well, this is just a constant. If it's a constant, then if you draw the picture, you get a circle. So this is the general case. Okay, singular. Although there is this the cross product is not going to be zero. Let me see why this is not going to be zero. Oh, yeah. Yeah. So this means it's constant. So it's a trivial case. Okay, it's definite. So that they just give a point. You locate a point. So in this case, the surface I call the surface is just a circle. Right? It's not a surface really. It's degenerate. Okay. Yeah, it's constant. You just locate. It's a point. It is a point. Here's a point. Okay, it's not a curve. When f, u, g all independent of u, then when you locate, it's just a circle. Okay, so that's it. All right, let's stop here.